So today has not much to do with turbulence, really. It's about models and instabilities. Models and waves. And my view of this is there are the question of models and how you approach describing the plasma dynamics. I mean, there are a trillion papers, there are multiple trillions of linear waves, and the idea, if you try to learn them all, you'll go crazy. And even if you try to learn the most general thing, you will have no physical intuition. So my approach to this is to study in depth a few simple representative cases and then build outward. So I don't use the fanciest theory, I rather talk in depth about a few simple things, and as I say, in depth. Then it's very easy to calculate kinetic corrections to this or that once you know what you're doing, okay? I should say my philosophy is in the minority. Many people say, oh, you have to start with the most general gyrokinetic equation and keep the gravitational pull of Neptune and all of this, and I don't agree. So I want to talk today about, particularly since we have a foreshortened time, I want to talk about two models in some depth. These two are related. They somehow have acquired the name of Hasegawa, but really other people did. This is the collisional drift wave, and this goes back to Sagdayev and Moiseyev. And you can see the Hasegawa-Mina equation sitting in the paper of Sagdayev, Shapiro, and Sarchenko. And while we're on the way, we'll touch briefly on reduced MHD, or what are called the Strauss equations. And once at an IAEA meeting, Boris Kavantsev got up after a talk where the Strauss equations were used, and he politely reminded them that they were really the Kavantsev-Kaluza equations, and they had done it 3 or 4 years earlier. So the point is, these models go by different names. These two papers are on the website. This paper is in POP, or well, it's really Physics of Fluids. It's an old one, 76. They're all in many books. Another thing on the website that is quite useful on the zoology of models, there is an old review by Kavantsev and Kaluza, 1970. Reviews of plasma physics. It's an oldie but goodie. I recommend it highly. And then there's a chapter from the book by Ito et al. So there's plenty of reference material. And then, with that, you can go off and read the current literature about fancier things. I think it's good to do non-fancy things at first. So the strategy is to build things up. Now, mean, the fundamental idea in low frequency turbulence, look, this is talking about the models, the basic waves, and what I'll call a little bit the fluxes. What comes out, okay? Anyway, the basic, the most fundamental idea in low frequency turbulence is the idea of quasi-neutrality. In other words, neglecting impurities. By the way, there are separate fluctuations have to be accounted for impurities. But the basic thing is charge balance, and the total charge has to be zero, right? Then by continuity, this implies that the divergence of the current has to be zero. That's really one of the most universal basic, that is the most universal basic equation, right? And in general, the current is the sum of a piece perpendicular to the field plus a piece parallel to the field, and I'll call I parallel the unit vector in the parallel direction. So we can write this equation as div perp dot j perp plus div parallel j parallel equals 0. And we can immediately write div parallel j parallel. What does div parallel j parallel mean? Div parallel j parallel, right, simply means this is the gradient parallel to the total field. So that's what I'll call B naught, the mean field, right, plus B fluctuating, whole thing dot grad, divided by the magnitude of the total field, right? And furthermore, we will be operating under the assumption that we at some level have weak turbulence. So we'll say B tilde magnitude is much less than B naught. So then we can immediately write div parallel j parallel, right, is equal to what I will call del parallel 0, right? In other words, the gradient along the mean field, j parallel, right, plus now B tilde over B naught dot grad j parallel. And if you could say what happens if I have an unperturbed current, right? So I could have something that would be B radial over B naught d by dr j parallel mean, right? Generally, we're not going to worry about that last one. Okay? So this is basically that the current has no sources or sinks. The currents are closed, right? Now, this is the easy part. What of div perp dot j perp? Well, you recognize this has to be equal to div perp dot j perp ion minus, well, plus j perp electron. And this in turn has to be equal to div perp dot. Now we start figuring out what's going on, right? So what is the primary motion of the electrons and ions across the magnetic field? E cross D drift, precisely. So, what? So, you would have, so then that would be N, let's say E for the ions, and then V E cross D, right? something else, which we'll leave blank for the moment. And for the electrons, we'd also have minus n. Doesn't really matter whether it's n fluctuating or n total, it's the same. You have n, e, and then v, e cross b electron, right? This is ion and this is electron, okay? Plus other things, which we'll leave blank in a moment, right? And the thing you realize immediately is that, you know, the E cross B drift is the same, right, for both species, right? So V E cross B ion or electron is just equal to C over B naught. The field is in the Z direction, E cross B, right? So since it's the same for both species and you have this handy dandy minus sign here, these two terms cancel, okay? So that means you have no current from the E cross B drift, all right? So in the simplest possible picture, what might, you know, you turn to next, right? What you might turn to next is the polarization drift. Right, you recall, you know, this is in the pig, you know, let's say the ion temperature is low for the moment. This is a simplification. I should add that this is in the fluid picture, you need that caveat. In the kinetic picture, you don't. I mean, the fundamental motion is across the field of particles is E cross B. So there's no ambiguity. But anyway, you know, if you write down the equation of motion, right, that you're used to, you have you have dV dt is Q over mE. Never mind the pressure for now, let's just look at the particle motion, plus Q over m v, and let me put the v naught out here and the c v cross z. Right, so the lowest order balance is to balance these two, right? And that gives the E cross B drift. The next order balance is basically to write, and this is total derivative of d E cross D, right? Substituting in there, then is equal to omega I, I'll just put omega for now, V cross Z. Right? So what I'm doing is I'm effectively doing an expansion. Right? You notice that this is of order gyro frequency, this is of order the frequency of motion. We're ordering the gyro frequency big compared to the frequency of motion. So the lowest order, so basically, let me write for an aside here. We write V is V0 plus V1 plus blah, 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 where the expansion parameter, this is of order frequency over gyro frequency, and we plug that in. So we have d by dt of V0 plus V1, etc., equals Q over ME plus omega V0 plus V1 plus blah, 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 cross Z, right? So now I think you see it, the lowest order, we balance these two, right? For V1, we balance d by dt of V0 with omega cross V1. So we have d by dt of V0, which is V cross V, and and this is equal to omega V1 cross Z hat. And this you will recognize is just our friend up here. Okay? All right, and that correction get it right, get all the wonderful little factors. That correction is the polarization drift. So that gives us, let me call it, boy, I can, use up space fast here. V perp 1, right, is equal to C squared over V squared E times mass times E perp dot. And that is a total derivative just written. Or maybe I should write this as d by dt of E perp. All right. Now there are a few things to immediately notice about this beastie. Okay. Now the drifts are different, and it's very clear. This is called the polarization drift. And it's very clearly evident that V polarization ion is much bigger than V polarization electron in general, right? Because you have this explicit dependence on mass here. Okay? And by the way, you can kind of see what's coming here. You notice this is going to be basically 1 over cyclotron frequency squared. So div perp dot V perp of this is going to be something like K perp rho squared in size. So the bottom line, going back to our friend here, we can put nothing here, and we can put V polarization ion, right? So then we have div perp dot J perp, right, is equal to N naught E times div perp times dV polarization ion. And that's the simplest expression for the perpendicular, the divergence of the perpendicular current. Okay. You notice now, so we can really write this over here for clarity. So we have getting somewhere, right? So now we've reduced, this equation is starting, and we can kind of, not worrying about all the little factors for the moment, we can maybe, the trick with these blackboards is to realize how to split them and shift them up, right? But what you have is, I'll let you fill in the garbage, but you have a mess, right, times d by dt, right, of the divergence of E perp, right? That's really what, and this mess is proportional to NI and various other claps, various other claps. Plus then our friend over here. From here on out, I am not going to worry about the current gradient. Just to make life simple, we're interested in micro. So this plus what amounts to div parallel 0, j parallel tilde, and this we can think of as a fluctuation per tilde. You know, I'm not going to put the hats on, we'll just call it like it is, plus b perp tilde over b naught. Now this one is, that is, j parallel tilde equals 0, right? And that starts to look familiar, right? So that's the basic equation, div dot j equals 0. Anybody, does that look familiar to any of you? It should. I mean, if any of you, I mean, let me suppose I wrote E as grad phi. Right? So we're always talking about kind of low beta regimes. So E perp is electrostatic. E parallel can be electromagnetic. Let me clarify that, right? Just so we know, right? E, last E, is equal to minus grad phi minus 1 over c dA dt, right? We all, I think, remember that vaguely from basic electromagnetism. So E perp, right, then is equal to minus del perp phi minus 1 over c dA perp dt, right? dA perp, A perp gives rise to parallel compression, right? In other words, A perp gives rise to delta B parallel, right? In other words, so that's like squeezing the equilibrium magnetic field. That's hard in the tokamak. That requires a very high beta plasma, all right? Forget that in general. I mean, maybe some of these spherical torus experiments might do that eventually, but nothing in the near term. So you can jump that. So E perp is grad phi. Now E parallel, right, is equal to minus del parallel phi minus 1 over c d by dt of A parallel. This is important. This will be what ultimately gives you the shear Alfvén rate. Okay, so with that, we can write this as del perp phi, and then this whole thing would go to del squared phi d by dt. Does that equation look familiar to anybody, given that? Well, that's one of the two reduced MHD equations, right? That's the curl of the momentum balance equation, or basically what you might call the vorticity equation in reduced MHD, right? I mean, it's just div j equals 0. If you had curved field lines, which we're not doing for the first pass, there'd be an additional term for curvature. But this is one of the two basic equations you need to describe a shear Alfvén wave. Okay? Notice in the shear Alfvén wave, you have two fields. One is the perpendicular magnetic field, or equivalently the parallel magnetic potential, A parallel, and one is the perpendicular velocity field, or equivalently the electrostatic potential phi. This is one of the two of them. All right, so this I'm going to call equation number 1. All right. Now, with all that said and done, what do you think equation number 2 has got to be? Well, speaking of, you have to do something about J, okay? And that brings us, I mean, really the key equation in most of these models, in one form or another, is what amounts to the Ohm's law. Right? And, you know, the basic story is all right, so what do you think the full Ohm's law is? The full Ohm's law is just going to be now E parallel plus something is equal to J parallel over some conductivity sigma. And the something is due to the electron pressure, right? You have to, you know, to incorporate the fact that there's now a parallel thermal pressure in the Ohm's law. Okay, so this would be basically E parallel plus del parallel PE, and then there'd be a factor of NE there, right? So this is understood in principle to be minus 1 over C dA parallel dt minus del parallel phi. And this guy, right, is understood to be, you know, del parallel pressure is N times T. So you would have NE times TE. We're just consistent with what we were doing before. We're just worried about electron temperature divided by N naught E, right? And then this thing is the current. And you notice then, and again, del parallel here has to be understood as V naught dot B naught dot del parallel, or just, let me put it this way, del parallel plus B tilde over B naught dot del perp. Okay? So this is the Ohm's law. You will note, by the way, a very important feature of this is that you have the ability to balance, you know, there are several balances here. There is E parallel equals 0, which is ideal MHD, and that's like the Shear-Alfvén wave. You have E parallel equals eta J, and this is resistive MHD. In other words, you could neglect the electron pressure term and combine, so I would say equation 1 plus these two, one leads to ideal MHD, one leads to resistive MHD, okay? However, there is another, shall we say, route forward, which is to take equation 1, right, plus the electrostatic limit, right? So that would be effectively, you know, J parallel over sigma, much bigger than d by dt of A parallel. Sorry about the squeeze there. Or just equivalently neglect the inductive electric field. So if you did that. So if you did that, then, right, you would be you could balance on the left side del parallel phi with del parallel p, or del parallel phi with eta j. Del parallel phi with eta j would just be resistive MHD. This other balance, del parallel phi versus del parallel p, what do you think that leads to? That is basic balance for drift waves, right? Because that's going to give you something like Boltzmann electrons, is the essential balance there, right? In other words, the zeroth order balance here would be something like minus del parallel of phi minus p equals 0. And remember, del parallel is just del parallel 0 now, and this would say, this would say basically the electron pressure to within a factor goes as the potential, and this is the Boltzmann balance. It's the Boltzmann relation, essentially. Okay? So, we're not really interested in NH2 here. But I mean, you see the point. You could, that you do have that possibility, but let me keep going before I start simplifying. Okay. And then there's a third thing. You need at least one more equation here. What is it? So we have, I'm going to call this thing here to be equation number 2, big equation number 2. So we have what amounts to a vorticity equation, and we have an Ohm's law. However, what has appeared in the Ohm's law is the electron pressure. So we need at least one more equation. Really, we need 2 more equations at a minimum. But we can get by with one. So what are the 2 more equations? Excuse me? Equation, yeah, close, but I mean, could you put it in more practical terms? You need an equation for the electron pressure, right? And I mean, so a minimum thing you need then is something like, right, really you need an equation for the electron pressure and the electron density and the electron temperature, okay? And we will be lazy and say, speaking of equation of state, the electrons are isothermal, so we'll just say P is equal to NT. This is just as a parameter, so then we need an electron density equation. Now, electrons are very closely tied to magnetic fields. So what we need then, for electrons, basically their perpendicular motion is just E cross B. So we have something like, if you just write the continuity equation for electrons, we'd have dN dt plus divergence of ND is equal to 0. And then we'd have dN dt plus V dot grad and average, right? And this would just be dE. We assume always we have some sort of profile with a radial gradient. And then we'd have something like N del dot V. And then divergence of V perp of VE cross B is 0. Divergence of V polarization isn't 0, but it's pathetically small since it's proportional to the electron mass. So this whole thing then just becomes del parallel V parallel electron, okay, equals 0. And of course, del V parallel electron we can recognize as minus J parallel over N naught E, right? So, we can then cleverly rewrite this equation as dN dt. But let me just save a little time here. Write this as a total derivative of N, right? Over N naught, whatever, plus, let me do that. Write it as a total derivative of N minus div parallel J parallel over E is equal to 0. And that's equation number 3. And these three equations have a lot in them. Then the fourth equation could be the electron temperature equation. That would give you 4 field models. There are a trillion papers. All of this stuff, by the way, is in Kadamsud and Kagusa, except they do it naturally. They don't make a big deal out of it. Then in the 80s, there was a whole series of papers kind of marketing it as a big business, writing, making a big deal out of writing these simple equations. So you'll see a lot of this stuff in the literature. For me, it's read Kadamsud and Kagusa, and you'll know it all. And then the other possibility is to keep the ion temperature finite, and then you would have an ion temperature equation, and that goes down the road to ITG modes. For today, we'll focus on electron drift waves. So, okay, we have 1, 2, and 3. Okay? So one can immediately kind of classify, I would make a taxonomy of models. Right? So if we had 1 and 2 together, and we made it electromagnetic, right? But we put n tilde, would basically ignore the density dynamics, we would have reduced MHD. And the basic wave that this kind of system would support is the shear Alfvén wave. With the current gradient, we could get tearing modes with that, retaining the current gradient. If we had versions 1 and 2 and 3, and with fully electromagnetic, then we would have what amounts to electromagnetic drift waves, which I'm not going to talk about. It's and the basic wave would be the drift Alfvén wave. And you can kind of see what would be going on here, right? Because you have 3 equations. They're each first order in time. You'd have 3 modes. So what would they have to be? They'd be the 2 shear Alfvén waves. Alfvén waves always come in pairs. And you'd have a third mode, which is related to the density gradient, which is the drift wave. You could, you could take equations 1 and 2, and you could, by the way, you could compute electrostatic corrections to that. Okay, so not electrostatic, resistive corrections. We are not going to be interested in these, but I just want to show you where they come from. We are going to be interested here on out in electrostatics. In electrostatics, you neglect, right, the time derivative of A parallel. You neglect the inductive electric field. So that means, in these equations, what does that tell? If you're neglecting the fluctuating A parallel, you neglect this, and you neglect the fluctuating B. So immediately, this equation simplifies to that, with that gone. This is just the fluctuating current. E parallel over here just becomes minus del parallel phi. Right? This, we've decided to say we're going to write, del parallel is now del parallel 0 entirely. This we're going to write as del parallel n and pull the constant temperature out here. And we have J parallel. and we have this guy here. Now you'll notice what we can do is we can solve for J parallel from this equation and stick it into here and stick it into here. Okay, so in this limit, right, of neglecting D tilde, neglecting the inductive electric field, we can write J parallel, and I should put isothermal for simplicity, so that we have a single electron temperature. I can write J parallel equals whatever from Ohm's law. And I can plug this into the vorticity and the density. All right, everybody see that? Right, and then I reduce the thing to two equations. Everybody see that? I can eliminate, you notice this guy by saying it's electrostatic, okay? And electrostatic, I mean, this is not just pulled out of thin air. Electrostatic is typically, you know, a comparison of the frequency in question versus eta k perp squared. So if it's cooler, right, more collisional, then it tends to be electrostatic unless the plasma beta is very hot. Right? If it's electrostatic, I get rid of all the fluctuating magnetic fields. You notice in this limit, the Ohm's law is linear. I can solve for the current in terms of the potential and the density and stick the current here into div J equals 0 and stick the current here into the density equation. Everybody see that? So now I have two nonlinear equations. I have a nonlinearity here, because it's a total d by dt, and I have a nonlinearity here. It's a total d by dt. So this includes, both d by dt's include advection by the E cross B velocity, okay? If I didn't make the electrostatic approximation, then the whole mess would be coupled to Alfvén waves, but that's another discussion. So you see, then I can reduce it to two equations, right? Equation for the vorticity and the equation for the density. Anybody know what these two equations are? You ever encountered them? Excuse me? Exactly. These are the Hasegawa-Wakatani equations. And like I say, I think Sadeyo did it first, but don't tell anyone. And these, in my view, are the simplest meaningful model of the drift wave, okay? They describe a collisional drift wave. So to So this brings us to what I would call the HW model. By the way, this was done late. You may have heard of the Hasegawa-Mima model that I'll talk about. This was done later, but in some sense is more, I think, more fundamental. Anyway, putting the pieces together and dimensionalizing. So again, going through what I said, in other words, taking the Ohm's law, substituting in here and in here, you get a vorticity equation, rho s squared d by dt of del squared phi, right? And here, by the way, phi is d-dimensionalized E phi over t, is a d-dimensionalized phi, equal minus d parallel del parallel squared, right? Del parallel is just the linear. So del parallel equals del parallel 0, and I'll tell you what d parallel is in a minute, times phi minus n tilde over n naught, right? And d parallel is equal to d thermal squared over nu EI. And sort of we picked apart the conductivity to get that. So that's the vorticity equation. And then the density equation. And then if you like, by the way, you can have a viscosity over here, nu del squared phi. We'll call that. A sub-zero means it's related to, and this should be perp. This is really perpendicular diffusion, to be precise. And in other words, it's exceedingly small. So that's the vorticity equation in the Hasegawa-Wakatani model. And the density equation is d by dt of n. That's the total n. And maybe to make it a little bit clearer, you could write this as n naught plus n tilde, right? Just think of it as a total n, plus our friend from the other day, v star. Well, if we do this, we don't need to put him in, so we'll just, I won't make him explicit yet, okay? Minus d perp 0, del perp 0, and tilde. I've neglected diffusion of the equilibrium. This is just pathetically slow. And again, on the right-hand side, minus d parallel del parallel squared of phi minus n tilde over n naught. And these are our two friendly equations, right? And it's understood that d by dt is equal to d by dt minus c over v naught grad phi cross z. So it's convect dot grad. It's advection by the e cross b velocity. Okay?
When you say vorticity equation, is that Laplacian phi exactly, if you like the full equation, is that Laplacian phi?
Take the curl of E cross B with grad phi, you'll get del squared phi.
So is that the omega, the vorticity?
Which
in fluid equation.
That's a component of the vorticity equation.
Exactly.
Yeah.
Omega. Okay.
Yeah, exactly. Del squared, I mean, in all these things, del squared phi, and it always comes in the normalized variable, it always comes with the rho squared, okay? This is equal to, this is always omega dot z if the magnetic field is in the z direction. Because if the basic velocity is E cross B, and you know that, say, from jumping ahead, the gyrokinetic or drift kinetic equation, the basic velocity is E cross B, then the curl of that will bend, you know? Yeah, that's unavoidable. So that's a vorticity equation. All right. Now this is an interesting pair of equations, to put it mildly. So, any questions on this? This is probably the most fundamental model, okay, as we will see. The reason for, by the way, you will note on the subject of vorticity, and you notice this has two fluxes, right? There are two nonlinear terms here. One is the nonlinear advection of vorticity. One is the nonlinear advection of density. So fluxes are very important because they describe transport. They also describe the coupling between the fluctuations and the mean field. So the two fluxes come, well, I'll just say it and we'll write it later. One flux comes from the advection of vorticity, and one flux comes from the advection of density. So the advection of density is the radial, this guy, which ultimately gives us the particle flux that leads to relaxation, and that's associated with drift instability. There's also a flux of vorticity, Vr del squared pi, and that is, we'll see, is related to the Reynolds force, and that is what generates the zonal flow ultimately. Okay? So you see in the basic equations, there's two channels for transport. One is transport of density to relax the system, and then one is